So my name is Tarek Bouazza, and this is my PhD thesis defense session, and the title is Contributions to Geometric Observer Design for Visual Inertial Navigation. Okay. So this has been a 3 years long project. We've done a lot of work and a lot of contributions that I will present later. I will first start with some motivations that led to these contributions. So the problem that we're dealing with itself is the problem of autonomous navigation. So the challenge of autonomous navigation is predominantly present today, and for robots it's quite challenging to perform perception, navigation, or mapping tasks in diverse environments. And so one of the backbone of autonomous navigation nowadays is what we call state estimation. And this enables robots to accurately determine their navigation state. So that's their position, orientation, or velocity, which is essential to operate in unknown environments. So why visual inertial navigation? So it basically comprises of two types of sensors. So the first sensor is a camera. So it's a lightweight, cheap, and easily accessible sensor, and it provides us with rich visual information on the environment. And then we have an IMU, which is an inertial measurement unit, which provides us with measurements on the motion of the robot itself, and that's angular velocity and acceleration of the vehicle. So these two sensors are complementary, and if we combine the measurements, then that will lead to low cost and highly accurate navigation systems. Okay. So visual inertial navigation is well suited to many applications, so like micro aerial vehicles, autonomous driving, underwater exploration, and different underwater applications. Also, it's present in wearables and health tracking devices, and in augmented reality and virtual reality experience more recently. So why geometric observers? So what we mean by observer or a filter, it's an algorithm that is designed to estimate the states of a system from incomplete or noisy measurements. So in general, we have a system which is a dynamical system that we have, and we want to design an observer, which is this algorithm that will estimate the state of the system. And we usually, in order to do that, we have to sort of design the estimate such that the error between the estimate and the state goes to zero or converges to something that we want. So in the classical designs, the system itself is a nonlinear system that we're dealing with. And in the classical design, we have this form of observers where we basically have an internal model of the system itself. And we have this term over here, which is the correction. And this term is designed such that this estimate and the difference between this estimate and the state converge to zero. But the problem is with this type of errors is not very suited when the state of our system itself lives in a manifold. So it's not really in an Euclidean space. And what happens is that this difference error is no longer well suited for this type of problems. So luckily for problems in robotics and navigation in general, the states for these problems actually live in a specific type of manifolds, which we call Lie groups. So what we mean by a Lie group is that it's a manifold that also has additional structure. And this structure is that, for example, we can multiply elements in this group in order to generate new elements. And we can also invert elements. And if we multiply an element by its inverse, we get the identity element, which is sort of the central element in the group. And so what geometric observers mean, it means that we can exploit the structure of these Lie groups in order to handle the nonlinearities of these problems and to improve the estimation performance of our observers. Okay. So in the introduction, I spoke about visual inertial navigation. And when we talk about vision, there are three particular problems that are of interest with monocular vision. And the first problem that is quite popular is the PNP problem, or the perspective endpoint problem. And in this case, we have a camera that is viewing some landmarks in a 3D environment. And we have information about the positions of these landmarks in the environment. So and this problem is called the PNP. When we don't really have the measurements of these coordinates in the 3D environment, we actually talk about relative pose estimation. So we're basically estimating the pose of a camera with respect to some other frame. There is a frame of reference that is like an initial frame for the camera. And as the camera moves, we estimate its pose with respect to this frame. Now, when the landmarks happen to lie on a planar surface, then we talk about homography. So the way this problem is solved is we estimate this homography matrix, and then we decompose it to extract the relative pose between the two frames. So a particular focus of this thesis will mainly be on the last part, which is dealing with homographies for this type of problems. Okay. So there's a set of contributions that I want to discuss in this work. So the first two contributions are essentially related to pose estimation. So we want to estimate the pose of a robot, and we want to do it using velocity measurements. Then we will extend this to inertial measurements, and we want to use homographies as our visual measurements to do this. And the rest of the contributions, the perspective will change. We will not be actually doing pose estimation, but we will be estimating this homography matrix itself. So we will basically design observers to estimate this matrix, and I will show you later why it's important to also work with homographies themselves. And in the last contribution, I will also talk about something we call polar symmetry, which can be also applied to estimate the pose of a robot for specific type of problems. Okay, so now I'll start with what we call Riccati observers. So as I said, we have some moving frame here, which is CT. So this frame is attached to the camera. And we have some reference frame, C0. And we have a relative position and orientation denoted by R and X as the relative pose between the two frames. And we also have a distance in a normal vector to this plane expressed in both frames. And so if we have coordinates between the points pi0 and rpi, which are expressed either in the moving frame or in the reference frame, these coordinates can be projected from one frame to the other using the homography matrix. And this matrix is this matrix over here, so this H, which is a 3x3 matrix that encodes the relative pose between them and the structure of the planar scene, so its direction and distance. So how do we solve this problem in general? So we have our kinematics for our pose. So we assume that our velocities are measured for now. So we have an angular velocity omega and linear velocity v. And what we actually get as measurement for this type of problems is the normalized feature correspondences. So basically, instead of working with the Euclidean coordinates, we actually work with spherical coordinates, pi and pi0 expressed in the two frames. And they are related by this constraint over here. So the problem is not very straightforward because we cannot really extract the position directly for this sort of problems. What we actually do is we estimate a scaled position. So we estimate this x over the 0 over here, and r and eta 0, and these are what we call the components of the homography. So what we're actually doing is we're extracting these components without necessarily knowing the homography itself. And in order to do that, we basically have our system, which is given over here. So this eta 0 here is a constant, the normal direction to the plane. And when we design the observer, we say we're not going to design it directly on this element on S2. Instead, we're going to over-parameterize it with some rotation matrix. So basically, I'm going to assume that my normal direction is a rotation of a fixed direction over here. Now, I will explain to you later why this actually works and what's the advantage of doing that. And so we designed the observer using this rotation matrix Q hat. And once we get this Q hat, we can project back the solutions to the sphere. So what remains now is to determine these sigma innovation terms, which are in red. And in order to do that, we have to define an error for our observer. So because we're working with a Lie group, one thing we can do is we can exploit the structure of this group. So R and X bar actually belong to a group we call the special Euclidean group. And this is a group of rigid body transformations. And we can use the structure of this group to define an error, which is given over here. And we also have the rotation, which is in SO3, and we can also define an error for that one. So once we define these errors, we can simply locally parameterize these rotation matrices with some vectors, which we call lambda. And the idea is if this lambda here goes to 0, then my error rotation will converge to the identity, which means that my estimate will converge to my true rotation matrix. So then what we have to do is we sort of linearize our error equations in terms of this linearized state that we define, and we try to get a matrix that is of this form. So we have a linear system right now with a matrix with a lower triangular form. And the tricky part here is in the measurement, which is defined using the homography. So this is a nonlinear measurement. So what we do is we multiply it by this H hat matrix over here. And this H hat is, in some sense, an estimate of the homography that we reconstruct using the estimates of our state. So then we also derive a measurement equation, and we get a C matrix as well. So this A and C matrix are quite important for the observer design. So then the way we design it is we implement it as a Kalman filter. So we have our input, which is our innovations, given by this following expression. And this P matrix is a solution to what we call the continuous Riccati equation, given over here. And we use a nice result from a paper on Riccati observers from 2017 by Hamill and Sampson, which says that if the matrix pair A star and C star which are these matrices evaluated at the origin, are uniformly observable, then we can actually achieve local uniform exponential stability. So what I mean by uniform observability now is given by this definition. So we say that the matrix pair is uniformly observable if this matrix W, which is what we call the observability gramian, is definite positive over some time interval. So if we manage to prove that, then we have the stability of our observer, and we know that the algorithm will converge. So what we need to do is we need to find conditions for this matrix pair to be uniformly observable. And in our work, what we managed to find is that we actually can find a geometric relationship. So if this condition is satisfied, then we have uniform observability. And it's actually on the number in the layout of the points on the scene. So I will define a consistent set. So this is basically a subset of at least 4 direction vectors, such as no triplets are linearly dependent. So in this example here on the right, we can see that this is a consistent set because there is no triplet that is linearly dependent. However, in this example, we can see that this is not a consistent set. And so if we assume that we have a consistent set, then we have uniform observability, and therefore we also have the stability of the observer. So something we actually can do is since we're only estimating a scaled position, we can actually retrieve the true scale. So we can estimate this S hat over here, which is the inverse of the distance, and also a gyro bias that we can also estimate. And the idea is we cascade another observer with this Riccati observer, and we can prove the global stability of the entire state. And this we can do it when we have velocity measurements. However, sometimes we don't have velocity measurements, so what we have to do is instead of using the velocity as an input, we're going to estimate a scaled velocity. So we can estimate this v over d0, but we can't estimate them separately. But it doesn't really matter for us. Okay, so just to show you some simulation results that we got, we simulate a camera that is moving in a circular trajectory over a horizontal target, and we run Monte Carlo simulations, and we display the estimation errors, and we see that all the estimation errors are converged. So these are the Riccati states that I've shown you earlier, and this is the bias and the scale that are also converging to 0. So then we decide to perform experiments, and in order to do that, we have a setup here in the lab. So we have a visual-inertial sensor over here, which is a camera in an IMU, and it's viewing this target, and we move it, and we record the motion using a motion capture system. So now we can compare to a ground truth that we have. So we do this, and we can see here, so in blue, we have the motion capture ground truth, and in red, we have our pose estimate. So these are components for the position vector, and these are the Euler angles for the orientation. So we can see that we get some small deviations over here. And this is because the moment we start actually moving in translational motion, what happens is the assumption on the constant velocity is no longer valid. So it still converges quite consistently, but there is some, we can see that there is some deviation between them. So a solution to this is instead of using velocity measurements, we can actually use inertial measurements. So we use the accelerometer that we have in the IMU. But this is not very easy to do. So we have our system as previously. Now we have to include the velocity as a state. So we have our dynamics so now we go into the second order kinematics, and we have this acceleration measurement that we can inject here, but we also have the gravity component to take into consideration. And for the gravity, we model it as some constant multiplied by some direction vector. And we do the same thing for this direction vector as we did previously. So we now design another observer with another matrix we call G hat, which is like the Q hat matrix, and we're going to apply the same trick. And we can also define the error using a group. In this case, it's not the spatial Euclidean group, it's what we call the extended spatial Euclidean group. So now we can also add the velocity into the group, and we can define our errors. And in order to design the innovations, we apply exactly the same principle as before. We linearize the system, then apply the Riccati framework. So we also now have to find uniform observability conditions. So we're also going to require the consistent set condition for the states to converge. And we use uniformly consistent, which is a stronger property that will not really detail. And we also need a persistently exciting condition that needs to be satisfied on the variation of the velocity. So this sort of says that the velocity cannot be constant. So there has to be some acceleration acceleration in order for this to be satisfied. And if this is satisfied, then we can actually estimate the depth, and we can also estimate the gravity. And so we have the local stability of the filter. So we run the same experiment, simulation, but this time we have like an inclined horizontal plane. So we have a gravity vector that is not necessarily known. We have a normal vector as well. And we also display the estimation errors. And we can see that everything is actually converging to 0. Okay. So now we can perform the same thing as we did before. We will do exactly the same experiment. So I will not really detail the algorithm, but in order to understand what we need is that we have the images. So we have to extract the features from these images, and then we get our PI and PI0 measurements that we need to get. And we implement the observer in a discrete format. So we have a propagation step and an update step. So in this propagation, we only use the IMU data to propagate the state. And then in the prediction or in the update, we use the visual measurements to make a correction. So just to show you, these are the results that we got for this one. So just to show you a video. So what we do in this case is we actually do what we call warping. So now I have all the states in order to reconstruct my homography estimate. And I can now evaluate my estimates using this homography. So the homography can be used to warp back all the coordinates into the reference image. So this is what we can do. So it's as if we have a constant image here, and it's the environment that is sort of moving because we're using this homography matrix. And at first, we have this motion over here, so we have this motion on the U. And then we switch back to other types of motion. And as these states are actually converging to the ground truth, I can reconstruct a homography matrix and then use that matrix to do what we call warping. So the idea is simply projecting back images from one frame to the reference frame. And it feels like the reference image is not changing at all. It's just that the environment is sort of moving. So I will not show the entire sequence, but this is sort of one of the many applications to homographies. This is what we call image stabilization, where we want to stabilize an image, and we can actually use these in like control problems and similar things. Okay. So for now, these are the contributions that I discussed for pause estimation by designing Riccati observers. I will now switch to a different perspective in this thesis, and I will not be talking about estimating the pose itself, but about estimating the homography matrix. So the first contribution in this sense is what we call a dense observer. So what I mean by an observer that estimates the homography using dense measurements is that instead of using features in the image, we can actually use the entire image as a measurement. So how do we actually design observers for the homography? So one idea is that the homography itself is defined up to a scale. So I can always inject some scale gamma over there, and this will generate always the same homography mapping. So I can choose this gamma in a way that will constrain the determinant of H to be equal to 1. And by doing so, I can ensure that this H matrix is in the spatial linear group, SL3. So you see we're working with a lot of Lie groups. This is one of the popular groups that we can work with. Now that we are working with a Lie group, we can do a classical observer design on a Lie group. So we can actually, so this element H has kinematics on the group. So it has these kinematics, H dot is equal to HU. And this U here is what we call a group velocity matrix. And it lives in the Lie algebra of the group, SL3. So this is basically a traceless matrix. So if this matrix is traceless, then this H will always remain in the group. So now I'll assume that this velocity here is measured, and I can design an observer for H. And this observer is basically an internal model, so I'm going to copy the kinematics of the homography, and I'm going to add another innovation term now, which is this delta. And I want to design delta in order to ensure that this H hat converges towards my H. So to do that, we also have to define a group error again. So you see, the interest of working with groups is we can define these errors on the group, and then we can use that to design our observers more accurately. And so by evaluating the dynamics of this error, we can find that it's actually autonomous, meaning that if this delta goes to 0, then the error does not evolve. And the idea is we want to design this delta such that our E goes to the identity, which means that our estimate H hat goes to the true homography H. So how can we design this delta? So the constructive approach is basically finding a suitable symmetry of this matrix on the output, so on the measurements that I have, once I find this measure, this action on the output, I can construct a corresponding cost function. Once I do that, I can use the gradient of this cost. So basically do a gradient descent in order to ensure that the error is converging to the identity. So a symmetry is essentially this map rho, such that if I have this relation over here, then it preserves sort of a symmetry with the homography operations itself. So just to give you an example of previous constructive designs, so this is what we call the feature-based homography observer. So you see that this, we will use exactly the same constraint as before. So we have this pi0 over here, and we can actually design our delta using a cost function that can be defined from this symmetry over here. And there's been a lot of work in this sense. Actually, there's been works on point features, lines, and also conic features. And for each, we can find a symmetry on the output space, which can then be used to construct a cost. And then we compute the gradient, and we find an appropriate correction term, delta. So what if we don't want to work with features? What if we want to work with the entire pixel information in the image? So one idea is instead of defining the action on the features themselves, you can actually define it on the intensities of the image. So the action of SL3 that I just showed you over here, this one, can actually be used to induce an action on their intensities. So instead of just mapping the feature points themselves from one image to another, I'm actually now going to map the intensity of the pixel, so the value of the pixel itself into another image. And we define this new group action here, which is defined as a composition of the image function itself with the other action on the feature coordinates. Now that we have an appropriate action, we can use it to do the design that I just showed you. So the way it works is I can define an error image. So I have my image over here, which is my image I. And this image is related to my reference image using H. So I can have an H hat inverse, which will take me to an error image, which I want to converge to the reference image. So if this H hat converges to H, these images will be identical. And now what I have to do, I have to use the difference between these two images in order to design my observer. So I can define a cost function. So this cost is given by this. So it's simply the difference, the difference between the two image maps. And we have this cost. The problem is, are we sure that this cost is non-degenerate? Meaning that when this E here is equal to the identity, is this really a global minimum for this cost? So we actually derive a condition for that. So if this condition is satisfied, which means that the Hessian of this cost is non-degenerate, then we know that the identity is a global minimum. So we have a proof of this. So now we can actually use the gradient of this cost function to design our correction delta, and we find the following expression. So this R here is the intensity residual, so it's the intensity difference between the error and the reference images. And it also depends on the gradient of the error image itself. Just to show you some simulation results. So we have a reference image here at time 0, and this is sort of our moving image using a generated homography. And now what we want our error image. So we're using a warping, as I showed you before. And the idea is if the estimate is converging accurately towards H, then this error image should converge towards our reference. And so this is what we see over time. So over time what's happening is it's actually converging towards this image, and the difference between them goes to 0. The problem with this is that so far we have made the assumption that we have measurements on this u velocity that I spoke about before. The problem is that this u is not really measured. In practice, we cannot really measure it, and we actually can even find an expression for it when the scene is static, which is given by the following expression. So it depends on the rigid body velocities of the camera, but not only. It also depends on the structure of the plane. So if the configuration of the plane is different, then the group velocity will be different. And this part here, I can measure using a gyroscope, but this part here I cannot measure. So one idea is I can actually split it into a measurable and unmeasurable components, and consider this gamma over here as a perturbation, and try to estimate it alongside the homography. So how can we estimate this gamma? We have to make some motion assumptions to simplify its dynamics. So for example, if I assume that the derivative of x over d is constant, which means that this is a motion that is a linear motion parallel to the scene or exponentially converging towards it, then I can design another observer for h and gamma together. and it's given by the following expression. So it's actually, we have a proof that we can actually use exactly the same innovation as before, and this still holds, and this gamma will converge to 0. So we actually implemented this in a simulation, just to show you a video. So here we have our reference image, and we can see here, so initially what happens is that the red here is basically the warped image. So we have this warped image here that is supposed to converge this on this reference, and this reference is basically a target that I have on my image sequence, and as I move in the video, I want this warped image here to converge towards this region of interest. And we can see here in red that as it starts evolving, the cost is actually decreasing, and we can see that the warping is actually good, which means that the estimate is converging towards the true homography. Of course, this is not perfect because the pixel coordinates are not exactly perfect. So what happens is we can see that some noise, so we can see that some vibration in the warped image that is slightly moving, but it's still converging towards my image. Okay. So far, this was the contribution for the homography estimation problem. So before they used to use feature coordinates directly to estimate the homography, the contribution was we can actually use pixel intensities. However, another issue is we still have to make these motion assumptions to estimate the homographies. So how can we avoid doing that? So I will present to you something we call the augmented homography estimation. But before doing that, I have to go into a little bit of theory into what we call equivariant filters to explain what it is actually. So what if the state of our system is not on a Lie group, but is on what we call a homogeneous space? So a homogeneous space is basically a space on which we can find a symmetry. So a symmetry is a group in a group action such that this group action acts transitively on the group, on the space. So to give you an example, the sphere S2, which is the space of all direction vectors, is a homogeneous space on SO3, which meaning that if I have some direction vector, I can rotate it anywhere using a rotation, and I can go to any other direction vector on the sphere. And so we talk in this side about what we call equivariance. So we say that the system is equivariant if we can also find an action on the input space, not really on the state space, which is this psi action such that this condition here is satisfied. So in general, what we mean by the equivariance is that if I have some point in the manifold and I transform it into another point, the idea is that the dynamics will also be translated, but the input will change. So there's also an equivalent transformation on the input space that sort of matches the action on the state itself. And we can also do this on the output. So if we have an output y, which is h of psi, I can also find a group action on the output such that if I transform my output, it equivalently transforms the state. And so we talk about equivariant outputs as well. So why am I presenting you this? Because if the system is equivariant, we can actually do a really nice trick which we call a lift. So what we mean by a lift is that I have my manifold over here, so my psi is evolving here, and my dynamics are sort of dictating where the state is changing. And instead of doing that on the manifold, I can actually construct a lift, which is a map that would take the dynamics into the group that I've been talking about, and then I can express the dynamics, so basically do the evolution on the group, and then project down the solutions back onto the manifold. And this projection is using this phi action on so it's sort of a map between the group and the manifold. And in order to do this, we sort of have to parameterize our manifold using the group. And for that, we have to fix an element here, which is this psi0. So if I fix an element, I can represent all the other elements, such as doing the dynamics on the group. Then I project down the solutions. And the lift actually verifies that I can always project down the solutions correctly. So it matches exactly the same trajectory. And we can now use this to design an observer or a filter. So how does this work? Instead of doing the observer on this homogeneous space, I do it on the group. So I define my dynamics here on, so now we'll be talking on x hat and not xi hat. And so I will be defining my observer here on the group. Then I can always project back my solutions so get back my actual state estimate using this projection here. And I can also now define what we call an equivariant error. So this error is a global parameterization now for the elements of the manifold using the group. So now that I can define this error, it's sort of equivalent to the errors I was defining on the groups, but now I have to use also the projection phi using the phi action to define this error. So then what I have to do is I have to choose some local coordinates around this psi0 and linearize them, linearize the dynamics in order to get sort of a linearized error system. And I can do exactly the same thing for the output. So I can define an output residual, and I can use the fact that I have an output symmetry rho in order to also construct sort of an output residual expressed in terms of equivariant coordinates. And then I linearize, and I have also a sort of a linearized measurement equation. And then I simply apply a Kalman filter for this linear system. So we basically propose an innovation, and this innovation is related to the continuous Riccati equation that I showed you before. So how do we apply this to homographies? So as I showed you before, the state for now was considered as H, which was an element of SL3. What if we extend the state such that we also include these two parameters here, d and eta, which are unknown? So if we estimate everything together, we can actually reconstruct the homography in its velocity. So this is what we do. We extend our state, and we also now, what we consider as input to our system is these v and omega directly. So now the rigid body velocities are direct inputs to the system, and now this state has been augmented. This is what we call the augmented homography problem. So we can actually prove that we have a symmetry group that acts on this space. And this group is given by SL3, SO3, MR1. So basically, I have a homography component here. I have a rotation component and a scaling component. And I can show that these group actions actually provide me with equivariance. So I can actually do a lift for my dynamics and design the observer on this group instead of doing it on the state space. So the calculations are a bit lengthy. The expressions are very long, so I'm not going to give them to you. But they're all in the thesis. So we run some simulations for this, and we basically run a Monte Carlo simulation where we have a camera following a Lissajous trajectory, and we can see that all the estimation errors are converging to 0. So even the normal direction and the distance are all converging to 0. So we actually did another extension to this work, which was instead of actually using velocity, so linear velocity is not really measured. So we're going to do exactly what we did before. Instead of using linear velocity directly, I'm going to use acceleration. And we can actually add the velocity into the state, and we also have to add the gravity direction into the state. I decided not to put this part in the presentation, but it's all in the thesis. And we can basically do exactly the same thing and design an equivariant filter for that problem. So in order to evaluate the consistency of our filter in this case, we compute what we call the ANIS, which is the average normalized estimation error squared. And this gives us an information whether this filter is actually capturing the distribution of the estimate or not. And we can see that the ANIS of this filter actually converges slightly below the value of 1. And in general, we want this ANIS to be equal to 1. So this is sort of the ideal value that we want. Okay. So now I'm going to go to another contribution of this work. So just to summarize, the first contribution was regarding estimating the pose itself. Then we went into the designing observers for estimate the homographies. And now I'm going to go back to the pose estimation problem, but from a different perspective. So I'm going to talk about what we call polar symmetry. And before talking about polar symmetry, I'll present to you epipolar geometry. So I spoke in the introduction about the different types of problems we have with monocular vision. And if the coordinates are actually in 3D space and not on a plane, we don't have a relationship between the points using a homography matrix, but it's actually given using what we call the epipolar constraint. So this constraint is always satisfied between the rotation matrix and the direction of the position vector and the bearing coordinates in the two camera frames. The problem with this constraint is that it's independent on the scale. And so because it's independent on position scale, it's not really compatible with Euclidean symmetry, where we have the rigid transformation with an orientation and complete position component. So how can we design an observer that sort of decouples the position component to have a magnitude and the direction, so that the direction part would only be included in the epipolar constraint? So one idea is to use, instead of representing this vector in R3, we can actually represent it in using a Lie group called SOT3, or the scaled orthogonal transformations group, which is a group of rotations and scalings. So basically, if I have a vector and I want to go to another 3D vector, I will simply rotate that vector and scale it to go to any other point in R3 except 0, of course. So we managed to show that we can actually have a group that acts on the pose space. And this group is what we call the polar symmetry group. So it's SO3/SOT3. And what it does is basically I have my position orientation here, direction in orientation here. And I can actually transform them into a new position and orientation, a direction of position orientation into another frame. And what's happening is that I'm also transforming or re-rotating the bearings as well. And this, what it does is actually preserve sort of a structure of this epipolar constraint. And I can use that to design an observer as I did before. So how can we do that? We simply lift the pose kinematics from this space onto the Lie group SO3/SOT3. And then we fix some origin R0, X0 at a choice. And we design the corresponding equivariant filter. So for this problem, we didn't actually stop there. We were actually able to analyze its uniform observability. So meaning, when does this actually work? And we end up with two sets of assumptions. So in these assumptions, if these are satisfied, which meaning that, so I need to have at least 5 landmarks, and they need to be distributed in a certain way. So I can't have them, for example, positioned on a horopter curve, and the origin of the camera lies at the origin of this horopter. So we have different conditions on how these points have to be sort of laid out. And if these conditions are satisfied, then we can actually recover the states that are related to the epipolar geometry, which are the direction of the position and the orientation. So this is very classical to the computer vision people. Usually they have 5 points. They can extract these components. However, what about the magnitude? So for the magnitude, we actually have a uniform observability condition for that, and it's the following persistently exciting condition. So if this condition here on the velocity is satisfied, then the scale component is also uniformly observable, and so the entire state is locally exponentially stable. And what this condition says is that the only motion that is not allowed is the motion that is on the axis that is relating the two origins of the frames. So if the camera moves like this, the magnitude is not observable. But it moves into any other direction, it will be observable, and I can estimate it. So just to show you, to validate this using simulations, we do a simulation according to 3 phases. So we have a phase with no motion at all, then with non-persistently exciting motion, so the camera will move on this axis, and then we do a persistently exciting motion. And we can see here that the error on the orientation in the direction actually converges directly. However, for the magnitude, so it does not converge at all in the no motion phase. And then it still not converges in the non-persistently exciting motion. But the moment we have a persistently exciting motion, we can see that it rapidly converges to 0. And the the associated Lyapunov function actually also converges to 0. And so this is locally exponentially stable. OK, so I finished with the contributions of this work. Just to summarize some of these contributions. So we basically designed Riccati observers to estimate the pose of a camera using homographies as implicit measurements. So we did not really have to estimate these homographies, but use them implicitly as measurements. We then proposed an observer solution that would estimate homographies using dense measurements. And another contribution was defining the augmented homography problem to design equivariant filters. And we do this using velocity measurements or even using inertial measurements. And the last contribution is on applying this polar symmetry group in order to estimate the pose by decoupling the position components into direction and scale. So just to talk about the perspectives of this work. So one of the perspectives is to actually use these pose estimates and integrate them into control design problems. So what is the value of having the estimates? The most important part is to use them in control applications. Another perspective is to improve the dense observer to match state-of-the-art algorithms. So for now, as it's designed, it's a bit raw for an algorithm, so it has to be improved and sort of robustified in order to match their performance. Another nice perspective is to investigate how can we actually do a visual inertial SLAM, for example, using this augmented homography EQF perspective. So the idea is that instead of estimating a pose like we do in a classical SLAM, we estimate homographies as we move, and we're also estimating sort of the structure of the planes in this environment. And then we use these homographies to sort of reconstruct the pose by extracting it from the homography matrix itself. This will be quite interesting to explore. And one last perspective is see what are the possibilities of extending the polar symmetry parametrization. For example, in visual SLAM challenges, we're basically decoupling this position into scale and direction, sort of robustifies the algorithms in some cases. Thank you for your attention.
Tarek Bouazza a présenté ses travaux sur la conception d'observateurs géométriques pour la navigation visuo-inertielle de façon très claire. Les jurys appréciaient la qualité pédagogique de l'exposé, qui était à la fois concis et dynamique. Tarek a su apporter des méthodes innovantes proposant de nombreux nouveaux observateurs géométriques. Les jurys soulignent la quantité du travail réalisé, qui nécessite des compétences à la fois en automatique et vision par ordinateur. Le jury a été impressionné par le spectre large du travail réalisé, allant des aspects fondamentaux de l'estimation d'état des systèmes dynamiques aux implémentations expérimentales. Les réponses aux nombreuses questions du jury ont permis de manière unanime de constater la grande maîtrise que le candidat a sur son sujet, ainsi que le recul qu'il a réussi à prendre aussi bien au niveau théorique qu'au travers du travail expérimental. En conclusion, le jury, unanime, décerne à Tarek Bouazza le grade de docteur en traitement du signal et des images de l'Université Côte d'Azur. Félicitations.
In the presence of my peers, with the completion of my doctorate in automatique traitement du signal et des images, in my quest for knowledge, I have carried out demanding research, demonstrated intellectual rigor, ethical reflection, and respect for the principles of research integrity. As I pursue my professional career, whatever my chosen field, I pledge to the greatest of my ability to continue to maintain integrity in my relationship to knowledge, in my methods, and in my results. So these 3 years have been life-changing for me. It was a very enriching experience. I learned a lot, and I met a lot of great friends. So I wish to thank all the jury that are here today and the ones that are online, especially Rob. Thank you so much. I know that it's like 2 or 3 a.m. Thank you. And I personally also wish to thank Peter and Rob and Mehduk and Claude and everyone I actually worked with. I learned a lot from you. I learned how to actually do research, and I'm very grateful for that. And in particular, of course, I want to thank my supervisor, Tarek Hamel. Yeah, it's been, honestly, it's been really great to work with you, both on a personal level and a professional level. So thank you so much. And of course, I wish to thank all my friends, and especially my friends here in the lab in Nice, and my friends back at home. Thank you all. And finally, I wish to thank my family and everyone that stood by my side. So thank you all very much. I think, I mean, on a professional level, an academic level, I learned a lot, but also on a personal level, I really enjoyed working with you. So thank you. Thank you so much. And,